Hi students, good morning to all. Today let us have a discussion the analytical part of complex envelopes of bandpass signal. So in prior to this session we have discussed what is Hilbert transform, what are the properties of Hilbert transform, and what is the pre-envelope. So what are the frequency spectrum, how we are going to represent in the positive pre-envelope as well as the negative pre-envelope. In continuation to this, let us discuss about the complex envelope of the bandpass signals. So first, we wanted to know how to define this complex envelope. For that, let us consider the bandpass signal, and this bandpass signal is denoted by S of t, and the Fourier transform of this signal S of t is denoted by S of f. So now the Fourier transform S of f is essentially confined to a band of frequencies. Okay, so that means of total extent, the maximum bandwidth is 2W, and the centered frequency can be plus Fc or minus Fc. This Fc is nothing but the carrier frequency. Okay, and in majority of the communication signals, the bandwidth 2W is very small whenever we are comparing with the carrier frequency Fc. Therefore, we can refer that, if this is the case, we can refer the signal as narrow band signal, that is S of t. Whenever the bandwidth 2W is less than the carrier frequency Fc, we can say that the signal S of t is represented as a narrow band signal. Okay, and the pre-envelope of the narrow band signal S of t, already we calculated the pre-envelope of the signal and how the S of t is represented. We can write it as S plus of t, that is equal to S bar of t into e power j 2 pi fct, right? So this S plus of t, we know that is S of t is nothing but a bandpass signal, and the pre-envelope of the bandpass signal is represented by S plus of t, and it is expressed in a way that S bar of t into e power j 2 pi fct. Okay, and S bar of t is the complex envelope of the bandpass signal S of t. So the magnitude spectrum of bandpass signal and the pre-envelope S plus of t and the complex envelope S bar of t can be seen in the graphical representation. So coming to this is nothing but our magnitude spectrum of bandpass signal. Okay, so here it is represented S into f of c, modulus of S into fc. Okay, and it has been given for the frequency which is centered at minus fc, and this is the frequency which is centered at plus fc. So here we can say fc2 plus w. Okay, and here fc2 minus w, and here minus fc2 plus w minus fc2 minus w, and the total bandwidth is centered into 2w. And the second, this graphical representation shows that the magnitude spectrum of the pre-envelopes. So this is for the positive pre-envelope and this is for the negative pre-envelope. Okay, so here if you go, this is the positive pre-envelope and this is the magnitude spectrum for the complex envelope. So it is very clearly shown that S plus of f, here you can see Fc, centered frequency for plus Fc, and Fc plus w, Fc minus w, and we know that here minus Fc will be 0. So in the pre-envelope we have stated that G plus of t. Okay, once again we can recall that expression for here, that can be written as G plus of t is equal to, G plus of t is equal to what? 2 into G of f. For what? F greater than 0. Then G of 0 for f equal to 0. And whatever happened for f less than 0, automatically the value is 0. So using this expression, we have represented the complex envelope, the magnitude spectrum of pre-envelope, that is S plus of F. Okay. So then this is the complex envelope, and the complex envelope magnitude. Then applying the frequency shifting property of the Fourier transform, the spectrum of complex envelope S bar of t is limited to minus w to plus w, and it is centered at the origin. That has been seen in this diagram. Okay, this is the magnitude spectrum of complex envelope S bar of t. Then followed by this, the complex envelope S bar of t of the bandpass signal S of t is a complex low pass signal. Okay. Therefore, mapping from the bandpass signal S of t to the complex low pass signal S bar of t are the three main conditions. Conditions are note. We need to follow that. The first is nothing but information content of modulated signal S of t is fully preserved in the complex envelope S bar of t. Okay, that is the first case. Then followed by this analysis. Analysis of bandpass signal S of t is complicated by the presence of the carrier frequency Fc. Therefore, the complex envelope S bar of t dispenses with carrier frequency Fc, making the analysis very simpler one. The third thing is the use of S bar of t will require and having to handle some complex notations like little bit confusable notations. S bar of t, e power j2 pi fct, s cap of t, s plus of t. So these all are some of the essence of the mapping from the bandpass signal S of t to the complex signal S bar of t. Okay. So here we clearly understood in pre-envelope we got one question like how we are going to eliminate the all negative frequency content. Okay, for that we told by introducing the idea of complex valued signal, and also here we have differentiate from that by introducing a complex envelope of bandpass signal by considering the bandpass signal with a narrow band signal. When we will call it as the particular signal is a narrow band signal whenever the bandwidth 2W is small compared to the carrier frequency Fc. That concept is applied over in the complex envelope. Hope everybody understood this complex envelope concept, and thank you for the listening or watching this video.